So if you just remember previous lecture, in that lecture we will discuss the dual problem of our primal problem. So we got our primal problem simple form a geometric interpretations, or simple to form a soft margin SVM. Just both are the same things. So simple primal problem we are got from there. And in previous lecture we see that how we are just simply converting our primal problem to a dual problem. We can increase our latency of our problem for a problem, and how important is that. So simple first write down what is our first simple write down what is our dual problem of this SVM. So in dual problem we have seen that we have to maximize our alpha I, that I is 1, I lies from 1 to n, alpha I minus 1 by 2 summations I is equals to 1 to n, summations also j is equals to 1 to n, alpha I into alpha j, and yi to yj, and it is xi transpose xj. Okay, we have seen that this thing, and we have also some constants such that our alpha I is greater than is equals to 0, and we have seen that our alpha I is equals to 0 for support vectors. We just discussed this thing in previous lecture. I am not again discussing. And we are support alpha is greater than 0 for non-support vectors. Just I think I am doing some mistakes. Okay. Sorry. I think it will have alpha is greater than is equals to 0 for support vectors, and is equals to 0 for non-support. And we are just find this thing. We are finding this thing in previous lecture. Okay. And because of this thing, we can easily build our a low latency. Okay. And also we have one kind of constant, that is I is equals to 1 to n, then alpha I yi is equals to 0. We have got this is our dual problem. Simple. Now simple, just focus on this part of the dual problem, just this part. If you just rewrite this thing, that is xi transpose xj, simple, this thing can be treated as a dot product of this one and this one. This thing is simple. If we just taking the vector from dot product, means is this simple this. Okay, just simple use the dot product. Both are the same thing. So simple dot product means what? We can in early lectures, if you just remember the cosine similarity. So simply cosine similarity means nothing, it is simply a dot product. So if you just compare this thing with cosine similarity of xi and xj, these two things are the same. Dot product of xi and xj is the simply cosine similarity of xi and xj, and it will works when our norm of x I is equals to 1, as well as norm of jsj is equals to 1. So this thing is simple one type of similarity, right? Okay, if this modulus is 1, then this thing is simply a cosine similarity. Okay, if this the norm of these two vectors are simple. So if you just see this portion of this problem, this is simply a similarity type portion. So this is simply a similarity portion. Easily we can write this is a similarity between xi and xj. These two things are the similarity thing. In other language, this similarity is, in other language we call this similarity in other language is a kernel. We can easily replace this thing as kernel between xi and xj. Okay, and in the next part of this series of lecture support vector machines, we can see the how the kernel trick works. Okay, simple, instead of this thing we can use, if we use the k of xij, so this formulation will convert it to a kernel trick. Okay, now simple, instead of using this thing, now I am here using the kernel. Just I am removing this thing. I am simple, instead of using this I am here using the kernel of xi, because of simple this thing. Okay, I think this thing is clear now. Now going to the kernel type. Okay, so just I am here comparing side by side this thing. I think then it will be okay. If I am used just I am using this kernel, I am comparing this thing. So if he, instead of k, such just in if you just remember the dual problem, instead of kij, instead of kij, if I used xi and xj transpose, that is we see in primal kernel simple, in our dual problem if we see it in dual problem, instead of kernel we are using this thing, this thing. So if we use this thing, then this thing we call the linear SVM. Linear SVM. Okay, and if we use, instead of this one, if we use simple this kernel function, this kernel function, then this dual problem is called the dual problem kernel SVM. Okay, simple, if we using this transformation xi into xj transport xi transport, I am writing some mistake, xi transformation xj, then here simple we are using the linear SVM. If we are using simple a kernel function, this thing we call the kernel SVM. Kernel function, then we call this function as a kernel SVM. Okay, so similarly, if we just remember our query functions, just what is our query functions, just write down our query function. So this is our x cube, I is equals to 1 to n alpha I yi. So we just in query function we see that here we are using x I transpose x cube. So instead of plus b, we are simple, see this thing in query function in previous lecture. So instead here simply, instead of this actually for linear SVM we are using this query functions, but in kernel SVM we are not using this function. Here we are using this function, kernel functions, kernel of xi comma xk. Okay, in the next part, in the next in this series, in the next lectures, we will see how the kernel trick used to handle the non-linear separable data. Okay, just if you remember our logistic regressions, we are using their kernel trick. Sorry, kernel means or features transformation trick, features transformation engineering techniques. How the non-linearly separable data using simple the features transformation, how it is simply we can separate this data linearly. Okay, in logistic regressions we see that. Similarly here also we can, using the kernel function concept, we can see how the non-linearly separable functions are simply are separable using this SVM technique. Okay. So the most important idea of the is, so the most important in the early 1990s, in the, if you just recall, in early 1990s. So it is the most important idea in the world of machine learning. So in the early 1990s, the most important idea in SVM is kernel SVM. Okay, this is the most important in the whole SVM. In the whole world of SVM, the kernel SVM is the most important. And linear SVM logistic regression is nothing. It is simple trivial thing. So just extension of this idea into a kernel concept, kernel using the simple kerning function, extensions of this idea, it is the most important. So simple, if you just remember our soft margin SVM, if you just see in soft margin SVM, it is in soft margin SVM, what we are doing, we are finding the hyperplane that will maximize our margin. In soft margin we are finding the hyperplane that will find by simply using the maximizing of the distance. So the we are simple find this hyperplane simply margin using the margin maximization technique. We are simply use the margin maximize. And it is similar type this concept and the logarithm register. If you just remember the logistic regression concept, these both things are the same concept, same kind of concepts, and this kind of things will work properly if our data is linearly separable or it is almost linearly separable. So this thing is not working for a non-linear separable data. Okay, so for linear SVM, we are using the kernel functions xi transpose xj, and for kernel SVM, we are using the functions k of xi comma xj. This is the main. Okay, so linearly separable, linear SVM, logistic regression, simple. These both things are both the things are same. Both the things are same, but it is not a main important thing. It is a trivial thing in regressions world. But the most important is the most beautiful, most interesting, most adventurous thing is the kernel. So let's see. So before going to the lectures of the kernel SPM, so just I am going to summarize this again. So in a linear SVM, okay, in linear SVM we are using the margin maximization hyperplane. Okay, just I am comparing linear SVM and logistic regression. Here simple, I am going to compare these two things. In linear SVM, what we are doing, we are going to the using the margin maximization concept to build our hyperplane. Here using this concept to build our hyperplane, and what we are doing in logistic regressions, just remember, if you just forget, please revisit our logistic regression chapter. Here we are using the minimize our logistic loss. Here we are simple using the technique of minimize the logistic loss. Okay, so we are using here to build, and both the things, if you just remember, both the things work in the xi plane, in the space of xi. Okay, in xi space, both the things is working on the xi space. This one is also working on the xi space. Both these things are working on our xi space. But the world changing idea, that is our main world changing, this is the most important in 90s, in early sorry, in 1990s. If you just 1990s to early 20s, this is the world changing idea. So this is the most world changing idea, is the kernelization. In this age, in this decade, is in 19 decades, this is the most useful classification technique, a kernelization technique. And simple in we will see that linear SVMs, logistic SVMs, logistic regressions, both these things are work on xi space. The simple this, but here kernel trick will work differently. Simple, this kernel trick is, if you compare this kernel trick similar as this kernel trick is similar as the features transformation techniques in logistic regressions. In logistic regression, both are the same kind of thing. Okay, now if we just consider, if you just take a picture, if you just take a data set, like, just I am revisit this features transformation concept again. If you just take a, suppose our one kind of data set is like that. Suppose one kind of data set is like that, and let's another kind of data set is like, okay, if you simply use the linear SVM or simple logistic regressions, so here no hyperplane can separate it, this feature. Okay, so suppose if these features is our if this one is f1 features, and if this one is f2 features, so no linear SVM, logistic regressions, no, this kind of techniques would fail to separate this data. Linear SVM, if you call logistic regression, these kind of techniques would fail. Would fails. Okay, this cannot solve too. So simple, in also in f1 and f2 space. Okay, but if you sample using the features transformation, if you sample here using the features transformation in logistic regression, we see if we just transform these features to f1 to f1 square and f2 square space, so just write on it. If we using logistic regressions and features engineering, features transformation, then both the things will easily success this technique, will easily separate this technique. Succeed, spelling double ed, I think the spelling of the succeed is okay. Okay, if you had some spelling mistake, please correct it. Okay, so logic, you will see that if you simple using the logistic regressions and some features transformations, then easily we can see this space, these features, this kind of non-linear separable data easily separable. So how we can do the features transformations? Here we are using simple this trick. Our features, instead of f1 f2, if we take in our features f1 square and f2 square, in f1 square and f2 square space, it is easily linearly separable. Okay, we can see in logistic regression chapter how it is. So similarly, kernel SVM, so simple kernel SVM, if we choose a right kernel functions, then this kind of nonlinear data also possible to separate easily. Okay, so in kernel SVM, by choosing right kernel, by simple choosing right kernel, so it is possible to find the correct hyperplane, okay, to separate this nonlinear data. So to choose the correct hyperplane, what we has doing here? So simple, we are transforming our xi space to the space of another one. Suppose let's call xi dash space. Simple, by choosing right kernel, we can usually convert this space to the this space, x dash space. So in this space it is possible to separable. In this space we can easily find, in this space we can easily find a hyperplane. We can easily find the hyperplane. Okay, so by sample we see that by sample using the kernel technique, it is possible to separate the non-linear separable databases, to separate it. You can easily succeed. Okay, okay, now the I think so in the next series, in next lectures, we will easily see how the kind of things are important. We will see various kind of kernel functions like polynomial functions, polynomial kernel functions, trigonometric kernel functions, exponential kernel function, logarithmic kernel functions. So there are various kind of kernel functions. By using simple this kind of kernel functions, we will see how it is important, how a linear SVM that cannot doing the job. So in a kernel SVM that and they easily can doing this job appropriately for a complex kind of data sets. Okay, so I think till now it is okay, and you know, if you have any problem, comment below. Or I think till now the lectures I have already discussed in previous lectures, I think everything is okay, all of you. So I promise you in the futures video I will discuss this thing more clearly, more visually, more geometrically, and I think by simply seeing this video you can easily enjoy the world of machine learning. You can easily understand the maths behind the machine learning. I'm here just giving the importance, the mathematics of the machine learning. Here I am not coming to the more details of the language part. So I am just I am giving the concept of the mathematics, how the internal mathematics each works for a complex data. Okay, so let's tune with this video. So we'll see in next video. Okay.